fact, quite a privilege to get a chance to talk at this wonderful event in honor of Masaru Nakahara. And Masaru and I have known each other for many years. I could put a number on it, but it would embarrass me as well as you. I think it's more than 30, let's say that, years. And we have had many common research interests involving water, involving the use of high pressure. In fact, he's one of the people who influenced me to consider pressure as a variable, and he's quite ahead of his time in looking at that. So one of the things that will be in this talk is, in fact, a discussion of water under pressure and how it influences some of the more conventional ways we think about water as a solvent in terms of hydrophobicity and hydrophilicity. So what I'm going to talk about is, as Nobuyuki said, hydration at the nanoscale, structure and phase behavior. So the kind of problem we're going to talk about is water where there's at least one, usually two surfaces that define a volume in which the water is contained, and necessarily then one has interfacial terms as well as bulk terms, which influence the thermodynamics of the water as well as the structure. And that's what we're going to focus on. The thing that I guess I should define, because the usual definition of nanoscale science is the science of small things that I do and not what you do. And that seems to be, that's related to funding considerations. But what I mean by that is something where the size of the relevant object is in fact typically on the order of tens of angstroms. That is bigger than molecular scale, bigger than the characteristic functional groups of a chemical, but small compared to what we usually think of as macroscopic. So it's a transitional region in going from thinking about things in terms of chemistry, which we have a lot of intuition about, over to something which is macro scale, which we also have a lot of understanding about since for hundreds of years already. And the question is how one makes this transition, and can you control the behavior at the mesoscale, somewhere in between, by controlling things at the level of molecules. Okay. So I'm talking about lengths that are of the order of tens of angstroms, or maybe as high as several times that, separations of surfaces which are tens of angstroms or less. And of course, in biology, this happens to be a couple of proteins, you'll see these again later. That's always the relevant length scale, almost, at least the governing length scale for self-assembly and things like that. This work is done as part of a collaborative program that's specifically funded by the National Science Foundation in the United States as a collaborative program. And it's this work I'm going to talk about is collaborative with myself and one of my postdocs, and Pablo Benedetti, who's a professor of chemical engineering at Princeton University, and one of his postdocs. And I just wanted to put in a plug for the center I have at Texas, which is part of a fantastic group, the Institute for Computational Engineering and Sciences, whose goal is to foster and provide infrastructure for interdisciplinary research, which is essentially computational in nature. It can be business, it can be chemistry, physics, climate modeling, all kinds of areas like that, but it provides an outstanding environment for all those people to excel. And it's a wonderful operation on our campus. So, why do we care? I think everybody knows why we care about nanoscale forces, because those are the ones that govern self-assembly in biology or control self-assembly in modern nanotechnology. So you want to make a certain protein complex, or you want to engineer a protein to form a certain complex. At some point, you get to the point where the separations of things are nanoscale, and that's what's going to govern your final arrangement. Or you could have surface patterning, people trying to make devices at patterning surfaces with chemical groups, and then getting things to adsorb on these in a certain pattern. This is actual data. The pictures on top are models, but laid over top of electron microgrids. And then this is an example of trying to use self-assembly that IBM is working on for making three-dimensional patterns in chip design using direct self-assembly rather than lithography. So it's very important to the relevant use of nanotechnology in the future. Okay. Another place where these issues of salvation at short length scales come up, I said, is in biology. And this is to make this clear why it's what some of the really fundamental, well-known properties of proteins exhibit this, and it'll come up again later, and that is the so-called protein folding phase diagram in pressure and temperature. It's well known that although the shape of this curve can vary somewhat, that there's basically an envelope which, if you could extend negative pressure, would actually form what people believe in ellipse, that is a closed area, in which in the interior you can get native structures, that is functional protein structures. And anywhere outside, they aren't functional. So you can lower the temperature or raise the temperature, and the protein will denature. Now, denature here doesn't necessarily mean, doesn't define what the structure is, other than it becomes structured in a way that's different from the one that works. Okay? So cold denaturation, heat denaturation, everybody knows about it. Some of you have heat denatured eggs for breakfast. But pressure denaturation is also something that's been well studied. But the fundamental understanding of what's going on in the water and the protein when you go to lower temperatures and higher temperatures and higher pressures is not well established. But what we've tried to do in our studies is, in fact, to do a series of studies that are systematic, and that's what distinguishes the work from the cutting. It's not we did this protein and then we did that protein. We start with a model surface, which is a real chemical surface, and look at variations in the chemistry of it. And when we do that, we can vary the thermodynamic parameters and the surface structure systematically, and then try to learn what some of the rules are. Okay. I'm going to start by talking a little bit about a single hydrophobic or hydrophilic surface to sort of set the understanding of how one makes relevant measurements in computer simulations. These will be. And then I'm going to talk about confining. Some people talk about a single surface confining it. It sort of confines it in the sense that the water can't penetrate it. But usually people mean two surfaces with a nanoscale gap that's filled with water or not filled with water. And I'm going to talk about hydrophobic and hydrophilic surfaces. These are all based on a model of silica, which most of you know can be made hydrophilic or hydrophobic depending on how it's chemically treated with water. Water will slowly hydroxylate, very slowly, hydroxylate the surface of silicon dioxide and form a nice hydrophilic system. One of the clay that is at the surface of the ground in Austin, Texas, where I live, is hydrophilic clays. And when it rains, on those occasions when it rains, they absorb water and they swell enough that it can break your house. And so these kind of things are actually quite important in some practical contexts. Okay, so systematic variation is the theme. And then I'm going to show you something which I'm actually quite pleased with, and that is we try to find a way to put the understanding of a synthetic surface like hydroxylated silica on the same graph with the protein. And I'll show you a protein-like surface that we modify in a very systematic way to make something which has a surface which we can then ask, how does this surface compare to an idealized hydrophobic or hydrophilic surface, even though its chemistry is proteins, that is amino acids. Okay? And I'm not going to talk at all about the methods and models except for maybe one slide. This is a fairly vanilla simulation, vanilla, very ordinary simulation. Okay? This is my one slide. For those of you who don't do simulation but hear about all the models in simulation that people use for water, typical P, tip 5, PE, W, tip ST2, SPC, SPCE. This is one of those, basically one of those models, except this one was published in 1933. Quite a bit before all the simulation started. This is by the Burdell-Fowler model. And the point is that even then, it was understood that the basics of water's behavior is that it has a sphere that's fairly hard, that the to each other. And then inside there's an electrostatic distribution on the hydrogens. And then the oxygen. This particular model has the charge center for the oxygen off from the oxygen atom position. So there's a charge actually up here, which is almost identical to the tip 4P model. So the 4 sites, 1, 2, 3, 4, with the sphere centered on the oxygen. In all the work that I'm aware of, that when one looks at the results, which of these models one use, I don't think this one's actually, I don't know if simulations are this. But no matter which model you use, you are not misled as to what the basic behavior is. Okay? You may shift a freezing point, you may shift a boiling point, but you don't change the rules. And so I personally am a big believer in using a simple model which is pretty well tested, and that one we use is called SPCE, which has only 3 centers and a particular set of partial charges. Oxygen and hydrogen. These OHs can spin around to form hydrogen bonds, so that's why they don't point all in the same direction. And if in a complete hydrophilic plate, every top oxygen site is hydroxylated. If I look at it from the side, it's like that. Okay. And then we're going to look at water up against one of these or between 2 of these as a function of separation. So if I take 2 of these and put them in, fill them up, the box up with water with 2 of these inside, it might look like that, where these 2 plates are sitting right there, but they've been eliminated for vision, okay? And then these are all the water molecules. And so you can thermodynamically adjust the pressure and temperature by setting the pressure and temperature of the whole system. And then the question is, how does the water in between here respond? It doesn't have to be, and it typically is not at the same density and structure as the water on the outside. But this way you can set essentially that the water in here is at equilibrium with the given pressure and temperature of bulk water. Okay. You can do that by tricks otherwise, but this is a very easy way to do it. So to give you a sense of the size of the charges, for SPCE water, the oxygen charge is about 0.8, minus 0.8, and hydrogen is about plus 0.4. These are the charges on our SiOH. So the OH is fairly similar. And this is based on a very old calculation we did, which actually reproduces the heat of immersion of silicon, hydroxide silicon water. Okay. So this is the basic picture you'll see over and over, and what you'll see different is how many OHs are on it, where they are. Okay, so first thing I'm really interested in, and I'm still working on, is making contact between a macroscopic description of hydrophobicity and hydrophilicity and a microscopic one, because that's what underlies our ability to sort of do the chemistry and predict what's going to happen at a larger length scale. And the easiest way to think about characterizing the hydrophobicity is through the contact angle, which is a very, very old idea. That if you put a droplet of water on a surface, it will beat up or it will spread out depending on how hydrophilic the surface is. And this is just to give you a sense of, so this is a fully hydroxylated surface. Now these are now infinite surfaces, they're not plates. That is, they don't stop somewhere, and that's just so that if it spreads out, it doesn't run to the edge. Okay. So this is the hydroxylated, this is the with no hydroxylation on the surface. So just SiO4 units. And this is a snapshot of a nanoscale droplet sitting on the surface. If you take this surface, this molecular group, and you simulate it for a while, it will map out an average structure. And from that average structure, you can calculate the angle, which I'll show you on the next slide, the exact definition, but the angle at which it meets the surface. And the same here. This is a snapshot from one with a contact angle, which is fairly large, typical of an alkane surface, and which is hydrophobic, and this is one with a fairly small angle, which is characteristic of hydrophilic surface. So this gives you a better picture. So you map out the density, which, and I'll only show you half of it because there's no reason to show you the whole thing. And then the contact angle is defined as this angle here between the surface and the tangent at contact. And that tangent at contact is computed from the average shape of the distribution. And as that becomes more hydrophobic, it becomes closer and closer to a spherical droplet. And so that angle gets bigger and bigger, with 180 being essentially an absolute lack of contact, except at a point, hypothetical, for a droplet. Yeah. So I've got this surface with these groups on it, and what we'll do is a little game where you think about simulations, you can play games with it to learn things. So you have these partial charges on the SI and the O and the H. We're going to scale them by a constant. So with 1, it's fully hydroxylated, and with 0, it's fully hydrophobic, those two extremes I showed you in the last slide. And then we plot out the density distributions that we observe, and we get a series. Okay? Now, it is conventional only because it's conventional. It's not something magic happens there. To define a contact angle of 90 degrees, that is when this droplet comes in and it's absolutely perpendicular at contact. So it's a perfect hemisphere in the absence of gravity. As the division between hydrophobic and hydrophilic. If you said no, it's 95, nobody can argue with you. It's just that it's conventional. And what you see is that as you change the polarity of the surface by scaling K upwards, so at 1, this is the distribution. It's very spread out. And at 0, this is the distribution. That's the hydrophobic case. So this has a contact angle of 105, and this has a contact angle of 20 degrees. But if you look at it in between, there's a continuous variation, and you can find where does it actually become 90. And that happens at 40% of the charge. So the first lesson is polar doesn't mean hydrophilic. It has to be beyond a certain amount of polarity before you can say that it's hydrophilic by this criteria. So the partial charges here are fairly significant. It's not as polar as a water molecule or as alcohol, but it's polar. Okay? So this gives us a way to actually measure the hydrophobicity on the macroscopic scale, and you can do that with a microscopic model. Okay. Now, one of the other interesting things is if you look at the orientational structure. So what we're going to do all the way through is try to look at the structure and the thermodynamic quantities and see if they tell us the same thing. Okay? And if we don't know what the structure should tell us, we can look at the structure and say, this is a signature of this kind of behavior. So this is a little sketch that goes back to the, when Nasser and I only had known each other for about 6 or 7 years. And showing the typical behavior of water because of its hydrogen bonding properties, how it orients at a hydrophobic surface. And what one found in this early work was that in the event that the surface was essentially a plane, and you couldn't wrap around it with hydrogen bonds, that they tend to orient actually with, they tend to throw away one hydrogen bonding direction and form 3 really good ones up in the bubble. Okay, so that's a character, that's sort of signature of a real hydrophobic surface. And if you look at the orientation of these hydrogen bond directions with respect to the surface normal, this kind of structure has a peak at 180 degrees, which is over here. So this kind of behavior, where this peak is those 3 directions that point up, and this peak is the one that points down. That's typical hydrophobic behavior. And if you do the same scaling, what you find is continuous variation of the average orientation, so that at this critical value that I indicated earlier, it's pretty flat. It doesn't really care too much which way it orients. And that actually is characteristic of a system which will fluctuate a lot because there's not a lot of free energy difference in different orientation. So the structure reports the same thing that the thermodynamics did in terms of the contact angle. Okay? So later on, I'll show some graphs like this, and you have to remember this, and I'll remind you about it. But this shape being hydrophobic, and the other shape being hydrophilic, where it wants to point 3 directions in, that's a hydrophilic, and 3 directions out is hydrophobic. So let's look at actually some water up against one of these surfaces, and we'll take the 2 extremes at this point, the hydrophilic and the hydrophobic. All OHs are filled in, and none of the OHs are filled in. And we're just going to look at a slab of water right up against the surface, about 3 angstroms thick, and map out its density. And the first thing you notice in all of these is there's a pattern, right? There's blues and yellows or whatever. This is because the surface is not flat. Real atoms are not flat. There are dips between the O's on the surface. There are dips where the water can fit in. And the main thing to look at is, this is actually at a negative pressure. This is about where this water appears to behave a lot like ordinary real water. So this is slight negative pressure. The hydrophilic one, you can see all these bright spots, the red spots are high density. And those are water molecules sitting down between 3 oxygens, so it can form 3 hydrogen bonds to the surface. It sits in between 3 and has typically 2 donors and 1 acceptor, or 1 donor and 2 acceptors to the surface. If you look at the hydrophobic surface in the same region, the water has moved away from that surface. And blue corresponds to, this blue corresponds to no water density. And you can see there's a little bit of protrusion, but not very much. Now let's turn on this very important variable, the pressure, that Masaru has spent his career really employing and utilizing, and move the pressure up to about 2,000 bar. And at that pressure, this is where we saw earlier today in Fumio's talk, the point at which water starts to act rather differently. And in fact, if you look at these densities, you would say, oh, this is more hydrophilic because you see the really intense amount of water density in these spots, more intense than the hydrophilic surface. What you can conclude from this is, one thing is that the compressibility of the fluid is different at different surfaces. Right? The fluid is much more compressible here than it is there. If I took these 2 pictures after putting them up like this and rearranged them and asked you to tell me which was the low pressure and which was the high pressure, you would have difficulty doing it. But here you would say it's trivial. And in fact, if you compare these 2, and I didn't tell you anything else, you might guess that this was the hydrophilic one. In fact, there are no hydrogen bonds between the water and the surface. Okay? So pressure blurs the difference between hydrophilicity and hydrophilicity. And it also reveals that water has quite a bit of difference in its compressibility depending on the interface it's next to. Okay? This is something that's actually become a theme in a number of people's research. This issue of fluctuations which go along with compressibility and hydrophobic surfaces. So let's look at this pressure variable. I told you the water at the surface was more compressible. This is a plot of the density of water in a gap between 2 plates of about 16 angstroms. I use nanometers when I write papers, but I'm old enough that I use angstroms when I speak. So that doesn't bother anybody. So 1.6 nanometer gap between 2 plates. And depending exactly where you draw the edge of the distance between the plates, you get different estimates of density. But the slope is the compressibility. And you can see this is the confined water, that's bulk water, and this is more compressible. But then you can ask, where does the compressibility show up? And where it shows up is not in the orientation very much. The orientation has a variation of 2.5 kilobars. And the orientation doesn't change very much. It wants to orient to maximize the hydrogen bonds. But what changes is the density. This is the density profile between the 2 plates as a function of increasing pressure. And the density does move in and up at the surface from low pressure to high pressure. If you take the hydrophilic one, it's really quite remarkable. It shows you how strong hydrogen bonds are. That in the hydrophilic one, the 3, so this is bulk, this is the, and this one is the hydrophilic surface. The slopes are really almost identical. Okay? This compressibility is essentially unaffected by being up against the hydrophilic surface. The orientational structure is essentially unchanged, and the density is slightly peaked, a little more sharply, but there's no shifts. This stuff it doesn't, 2.5 kilobars does not move it around at all. And I think this is actually one of the most striking results that we have, is showing how resilient a hydrogen bonded network is to pressure when it comes to how it wants to solvate its surface. Okay, so this is the pressure variable. Let's go on and look at some other things. So first I'm going to look at some pattern surfaces. That is, ones in which I don't fully hydroxylate or fully not. So these are complementary surfaces. You can see the OHs here, the white dots. And here, it's the OHs in the opposite set of locations. And same thing here. There's a little gap in the middle, or here there's only 3 OHs. Or this one has an edge of OHs, and this has one, these are not complementary, but they're extreme. 1 OH in the middle. Now you can say 1 OH in the middle of 10 square nanometers, how could that have much effect? Well, when you start looking at the density, so this is the surface, the complementary surface. This one is the fully hydroxylated, and you saw that before. This one is the patch. So there's the water hydrating the patch, or the water missing, if that's a hydrophobic patch. One thing that you notice in this one, which is quite interesting, is that given the fact that over here there's no hydrogen bonding groups, and in the middle there are no hydrogen bonding groups on this surface, you see the very bright red on the edge. That is, the water will hydrate more strongly a group that is at the interface with a hydrophobic patch than it will one in which the choices are equal everywhere. And here's the one with 1 OH stuck in the middle. And you can see not only that it's fairly well hydrated, but there's a brightening here everywhere compared to there. That is, there's a higher density of water everywhere in here. And it turns out that is due to the fact that this water tends to often form strings of waters that go from here to the bowl, here to the bowl. But where that string is, of course, depends on it moves around in time. So there's water sitting there connected to the bowl typically by a string of water molecules, and it raises the average density everywhere. This one has a missing OH in the middle, but you can't see it. I bet anyone, no one in the room could tell me for sure there was a missing OH there, except by the fact that next to it there's even more well-hydrated OH. Again, this enhancement effect. So, now this is just a pressure thing again, even for these pattern surfaces. This surface versus that one, you pressurize it and you can't really see where the hole was. Right? This one is that surface and this is that surface. And it's very hard to tell which one has OHs missing where. Pressure gets rid of this difference in hydration. So now let's turn to temperature and see what happens. And the main conclusion here is that for many properties, lowering the temperature and raising the pressure have very, very similar effects. So this graph, this is a set I showed you before of the pressure response of water at one of these surfaces, the compressibility, the orientation, and density. So you should recognize that. This is at 300 Kelvin. Okay? If I then take the system at this one negative pressure, okay, slightly negative pressure, which just as I said is a useful place to compare things from, and I lower the temperature from 300 down to 220. These are not simple simulations, because when you get to very low temperature, it is very slow, and you have to run very long simulations, but it's not out of the reach of it. So this isobaric cooling at this low negative pressure, and then you can again do density versus the independent variable, which is not temperature, and you can see this is bulk water, the temperature of maximum density, which for this model is up here is I think 250 K, and this is the hydrophilic plates, and this is the hydrophobic plates. So again, the hydrophobic plates have the most density variation, and therefore the most variation in the density with temperature. And you can see that actually both of these surfaces remove the temperature of maximum density. At least it's either not there or it's at a temperature below 220. You can't tell that because you can't go down below very easily. The orientational structure, again, doesn't change very much for a hydrophobic system as a function of temperature. It's a little bit sharper at low temperature. And there's the density profile. So this is, room temperature going to low temperature. This is room pressure, atmospheric pressure going to high pressure. There's enormous parallelism. You can even quantify that lowering the temperature, which, remember the cold unfolding situation, you lower the temperature, proteins unfold. You raise the pressure, proteins unfold. The surface is more well hydrated at low temperature and at high pressure when it's hydrophobic. Okay? So this parallels this expectation that proteins would become less stable under these conditions if you accept the long-standing point of view that the main source of this is hydrophobic hydration changing from a strong deterrent to unfold into a weaker return to unfold. So let's look at this structure. Now you're familiar with these kind of pictures. So here's two surfaces that are complementary and where the OHs are. This is room temperature, where you can see good hydration of the patch, good hydration of the edges. You lower the temperature, and now you see much more similarity. The water has moved in to the hydrophobic regions much more completely at low temperature than it did. Now this is not pushed into it like a high pressure. It just means that these areas are much more readily hydrated when the temperature is low and high, and that's exactly what this protein unfolding thing refers to. Okay, so now let me talk about my last topic, which has to do with hydration when you have two confining surfaces which approach each other. And I'm not going to go through all this stuff. This is basically state-of-the-art 19th century theory, which says that, and there's a series of modern papers that have developed the idea, starting in 1988 with Bob Evans, and that is that when you have a slab of water, there are volume bulk terms and there are surface terms. As you bring the gap smaller and smaller, the amount of bulk material decreases. And if the water doesn't like the surface, at some point it will become more favorable for this water to vaporize in the gap than to remain there as a liquid, because it can gain that free energy back by being outside as a liquid. And this is a formalization of it in terms of Young's equation. I actually looked up Young's paper in which Young's equation is written, and it's not there. There's no equations in the paper that's quoted as Young's equation, which I found interesting. We never get through the referee process now. But so there's a critical distance as you bring these together, when the surface term will win out over the volume terms, the bulk terms, if the surfaces have a contact angle bigger than 90 degrees. Thermodynamically, that happens apparently at a very long distance, and in fact, kinetically, it happens at a much shorter distance. But I'm just going to try to look at real surfaces and determine the issue of when they are dry and when they are wet, as you bring them together. Dry surface, when they're close together, is a very focused surface. Okay? And there's a lot of literature revolving around paper by Lung, Chandler, and Weeks, which I'm not going to get into unless somebody wants to ask me about. The dynamics, therefore, is a big open question, when these things actually do this. The problem is that the barrier, the free energy barrier for the formation of a vapor, involves a very large reorganization of the solvent, and therefore it's very slow to happen, and slower as you make the distance between these bigger, and you have to form a much bigger vapor layer. Okay. So we take our system with two plates, and they're both now hydrophobic silicate. If they're hydrophilic silicate, it's not an issue because it's always liquid in between. And you bring these two plates together as a function of their separation, and as a function of the pressure on the bulk fluid, so the water in the gap is at equilibrium with the bulk fluid. And this pressure refers to the bulk fluid. And you take different separations and different pressures, and you examine what is the state of the water in between. Is it a liquid? Is it a vapor? Or is it in fact a solid, which I've done a lot of work on, but I'll come back to that in a second. And so there are a series of points. Each of these are fairly extensive simulation. And then there's a line here which just indicate roughly a liquid-vapor coexistence law. And it's not in temperature and pressure, it's in pressure and separation. And I told you as I make the gap smaller, it favors the vapor phase. And so you can see that as the gap comes down, you get more and more likelihood of vapor. And so there's this coexistence curve. This one point, I'm going to put down here a picture of what happens. So you start it filled with water, and in a few hundred picoseconds, the water leaves and goes out, except for a few fluctuations. Okay? And so you can see there's at a high pressure, it is the vapor extends to, at small gap, the vapor extends to high pressure. At larger gap, you have to, at a lower pressure, you can jam water interface. But at a small gap, the water does not want to go into the small gap capillary force. This over here is interesting because this is a region in which, and this we verified by going to other conditions, a region in which the water in between the surfaces crystallizes. This is a picture of the water crystal in between these two surfaces. This is a little bit defective. It's a two-molecule thick hexagonal cluster of water molecules. You're looking at two layers looking in on it. And this is an ice. Diffusion constant is very low. And the most amazing thing about it is this is at 300 Kelvin. A spontaneous formation of an ice at 300 Kelvin. This has been documented in a number of cases. If you go to higher pressures, you can get this to happen at bigger separations. And you can get more ice in different conditions. This spreads out to higher pressure. So what this tells you is that you shouldn't have bias in your understanding what the thermodynamics should be for this water. It's not like bulk water. I mean, if somebody said to you, I've got this way to make bulk water freeze at room temperature, you would take them off and get this some help from a doctor. Right? Once you have the surfaces involved, it changes the rules. And this is actually the lowest free energy state at this high pressure when it's confined. All right. So let's go and ask if I understand this for the two hydrophobic plates coming together. This is the coexistence line. If you go at room pressure, ordinary pressure, 1 atmosphere, basically 0, and you start bringing the plates together, when their separation is about 7 angstroms, the water will evaporate, spontaneously evaporate, and you have a vapor between. Is this the way you should think about two protein surfaces coming together? So in my last 6 minutes or so, what I want to talk about is a protein model, where we can do the comparison of the protein model directly, as I indicated. So this is a system I've worked on off and on for 10 or 11 years now. Only a few papers, but and I first learned about it from the crystallographer who did the original crystal structure long before I started to work on it in the 80s. And melatonin is what's called an amphiphilic protein. It forms a helix in which one side is hydrophobic and the other side is hydrophilic when it's folded. And it dimerizes in the crystal at least to form this thing, which consists of two antiparallel helices. And it forms one side which is largely hydrophobic and another side which is largely hydrophilic. Okay? It's found in the venom of bee stings. It disrupts membranes and it kills cells that way. That's how it makes your hand hurt if you get stung by a bee. In any case, it forms a nice model in the sense that you have this hydrophobic patch here. And that's what we had looked at before. Since this hydrophobic patch, although it's not flat, it is certainly not something you can wrap in a hydrophobic collaborator. And so that's why we had studied it. And this is what the electrostatic potential looks like when mapped on the surface. So this is the contact surface, the Leonard-Jones surface, which I've colored it by a scale which corresponds to the electrostatic potential of a test charge, and it goes from plus or minus 5 kT in strength for a unit charge in this grid. So red is one extreme and blue is the other. White would be no electrostatic potential. Okay? And as a reference point, this is hydroxylated silicon, where all these red dots are the hydrogens that are flopped around in different positions. So this is to give you a sense of what hydrophobic looks like when mapped this way. The problem is it's not flat, and I don't know quite how to compare it to the other system. So I'm going to do something. First thing I'm going to do is I'm going to remove these bright red things that are around the edge. Those are all charged groups that are on the terminum of these helices. And I want to have something that doesn't have those because it might mess up the comparison, might make the comparison more difficult. So I'm going to, since they are terminal groups, I can remove them. And with them, they're counter ions. And that's what this is. So it's still bumpy, but it is not with these charged edges. Then I'm going to take this and I'm going to flatten it. The way I do that, I take this whole system and I find each amino acid and I take the outermost atom of that amino acid and I move it forward until it reaches the plane of the outermost atom in the whole I do that for each residue as a whole, and I pull it forward and I get this surface. And if you look at the electrostatic potential of this surface and that one, they're very, very similar. It doesn't mess up the character, chemical character of the surface, because I'm moving the entire side chain and its backbone together when I create this flat surface. And this is, again, the reference point, the hydroxylated silica. Now, the clear is much less polar than this group. Okay, so this is a side view of two of these things up against each other in the geometry as they form in the crystal. And I'm going to show you real quickly what, this is the only, so you get a sense of what flattening it does. In the native structure, which I said I didn't really know how to compare to the flat surfaces of silica, these things conform to each other and wrap around. I think it looks like two cousins hugging each other. And in this case, I have this protein chemistry on the surfaces, but they really look very flat. So I can look at the water in that gap and put it on the same picture with the water between the hydrophobic silicas. And that's what I've done here. So this is just a schematic to give you a sense of what the two protein units look like, and the region in the middle, which is purely hydrophobic. By any protein chemist will tell you this thing's held together by hydrophobic interactions, and the area in the middle is a hydrophobic content. And I've showed you the silica, which is hydrophobic content, and I want to see to what extent are they similar. If you take these things and move them together, when it reaches the point at which the amount of space in here is just enough for one water molecule, you lose a little bit of water at the center, as you can see here. This is a slab of water between them, and just in the very center there is some loss at 5 angstroms per gap, which is just enough to fit a water molecule. If I make a hydrophilic, that will fill in. We did that calculation, put a hydrophilic residue right there, and it fills in. To show you how sensitive that loss is, this is the same calculation done at the same gap. Instead of zero pressure, it's 0.05 gigapascal. And this is the same calculation, 1 angstrom bigger gap. So you can see that that water loss is just very marginal. Now you say, okay, that sounds like that means they're less hydrophobic than the other plates, and that can be quantified. So now I look at the disk gap and the pressure, and I find where does this transition occur between liquid and vapor. And we do large numbers of simulations at different conditions, and if I start a fill, does it empty? And this line is the silica plate line from that earlier slide. And these points are those calculated for the protein plates. And it's completely obvious that the right coexistence line, or the right point at which the water and vapor would coexist, is shifted to lower pressure and smaller gaps. So you have to go to an absolutely minimum gap over here before, even at negative pressures, before it will dry. And in fact, these points here are points at which these red triangles, those are points at which the water itself is unstable. It will explode into vapor, even with nothing in it. Okay? So this point, which is liquid, is metastable. But these points at that low pressure, or this point at that gap at low pressure, water cannot extend. This water does not stay stable. It basically explodes into a vapor, which is an interesting simulation when you watch it, as it turns into vapor in your body, starts to become macroscopic in size on the computer. Okay, so this is pretty definitive, and in fact, this was the main goal of what we were trying to accomplish. That is, find a way to put a protein and a well-defined reference system on the same graph, and then be able to say, a standard hydrophobic surface in a protein is it more or less hydrophobic than this model? And clearly it's much less hydrophobic. And there are very people who have gone by that point of view before, because there are lots, you can't make a protein At least the backbone is polar. And there are polar groups behind this non-polar surface, and so on. This makes it quite clear that there's it would be quite extreme conditions before this liquid vapor transition would make a contribution to protein folding if it was this kind of surface. So I will stop there. The big question that isn't answered by this, the biggest question that's not answered, is the dynamics. As this comes together, as surfaces come together, do they ever have to enter this region in which you have liquid and vapor, or does the self-assembly occur more quickly than that? Are there dynamics of fluid flow and so on which affect the self-assembly? And that's the primary thing we're working on now. And once again, I'd like to thank everyone for the opportunity to be here on the occasion of honoring